Hello, welcome back to a crash course in circuit theory. We basically have completed the simplified microcontroller model. I would like to make a few comments regarding this model in terms of its limitations. As you can see at the very beginning of the input, we have a switch connected, and this switch operates in two positions, open or close, which we know represents a digital signal. And the output of the microcontroller is controlled by programming to determine whether the switch is open or closed, will then in turn will control the output switch position. And again, it's also two options, which gives us a digital output signal. So at this point, we can say that this is a complete digital control system because our input is digital and our output is digital. For analog voltages, we would need a lot more components around this simplified microcontroller model. I will not cover that in this video series, but I will talk a little bit about analog control when we discuss the driver circuit subsystem and the signal conditioning circuit subsystem. I will also direct you to some reference information that will help you with this process. But the main idea is that you understand how the microcontroller electronic control system works. Another aspect, another limitation that we have to consider when we're using a microcontroller in our project is current. There are limitations as to how much current that this microcontroller can provide to an output load, which means that if you need more than the specified current, then you will have to use some other technique to provide current for higher loads, such as motors and speakers and other high current devices. Also, we got to be very careful as to what we connect to our input, because if our input has too much loading, then it will also draw too much current from the microcontroller when it's in the open position, and too much current will flow out. I like to indicate that there are two options for voltage and two options for current at any point in a circuit. And this is how I summarize this. I say if you have a point in a circuit, then you can measure the voltage at that point, and that voltage could go up or the voltage can go down. Of course, when we say we're measuring a voltage at a point, what we really mean is that we're measuring at that point X, and there's another point in the circuit called ground, and we're measuring the voltage between Vx and Vy. So we call that Vxy. But since this value here doesn't change, then we can simplify this as Vx. And again, that voltage could either go up or down. Something else is available in a circuit, and that is current. And if you have connections like this, current can either go out of a particular point or it can go into a particular point. Okay? If it comes out of a particular point, we say that that point is acting as a source of current. And if the current is going into that point, we say that point is acting as a sink for current. So when we talk about a point, we can talk about the voltage level at that point. It can go up or the voltage can go down at that point. We also can talk about the current coming out of that point, or the current going into that point. This will become very important when we talk about the limitations of particular devices, components, and modules in our design. The subject that I'm talking about here is called interfacing, and that is when we try to match up the voltage and current levels between devices, components, and modules. And we have to look at these four elements. I call these four elements the IV matrix. So for every point in your system, for every component or device or module in your system, you need to be very clear about the IV matrix range for that point. The IV matrix range for that point. And usually you get this information either from experimentation or by studying the details of the data sheet. The next video, I'm going to talk about the symbols that are used in microcontrollers, in electric circuits, and to understand the general nature of those symbols and how it relates to the IV matrix.